Welcome back. Today will be the most interesting lecture, week 9, lecture 3 on probability theory with actuarial applications. We will settle the problem of approximation of discrete random variables by continuous random variables, and therefore why we will understand the philosophy behind giving this continuity correction and how to use it flawlessly. So, let us set the context by asking why do we require continuity correction. Now, here is the brief intro, that if we have a discrete random variable, you have a specific probability mass associated with that point. That is what you are looking at on the left hand side, where x is equal to 40 has some area under that bar. Okay, and the probability of x equal to 40 is strictly greater than 0. When I have a PDF, that area probability of y equal to 40 is 0, but this area that is covered by this particular probability is covered in the unit interval, because it is the rate of change of probability, if you remember, right. So, whenever I am talking about random variable, continuous random variable having a single value, I will say the probability is 0, and when I am talking about discrete random variable, I am saying it has a positive probability. So, when I have x equal to 40 and y equal to 40, I cannot equate them. Okay. So, it will never give me the exact values. So, what should be the solution? Because this particular probability, when I am handling PMF, the point is split over unit length, right. So, the solution is we must approximate the area of the bar with area under the curve over bar's width. Okay. So, this is the idea. Rate of change of probability should be considered integrated over that width. Width is generally unit. So, we have to understand it in that perspective. That means what? If I am handling a point at 40, I will look at unit length around that point 40, which is typically, if x is equal to 40, should be distributed from 39.5 to 40.5. Okay. So, that is the crucial understanding that we require for splitting that point mass. Okay. That is what we will call as 0.5 continuity correction. So, when a discrete bar that is given to you has a value 40, it is not just a line, it is a block that owns its space from 39.5 to 40.5. Okay. So, now with this in mind, if you look at probability of x is equal to k, then you will actually split that over k minus 0.5 to k plus 0.5 and approximate with this bell shaped curve. That accounts for the missing of this probability, this area above this. Okay. This will come into the area that is covered below this. Okay. So, with this understanding, we can actually correct the approximation of discrete values with continuous distributions. That is what the main purpose of this lecture is, and therefore, we need to set a proper rule or rule book for this kind of approximation. When can I go half length below the value, when should I go half length above the value, all those rules should be properly defined. So, let us define those rules in one shot, because the key confusion is whether I include this bar or exclude it. Okay. So, we will ask that question, do I want to include this bar? For example, if a question says probability of x less than or equal to 45, that means 45 bar is actually included. So what will you do? Now you have to accommodate this 45 bar, right? So if you chop it at 45, because the probability mass which is distributed, probability mass which is focused on 45 is distributed between 39.5 to 45.5. So what will you do? You will take it into account, which is 45.5. Now another interesting part will be, if I am asked x is strictly less than 45, shall I go up to 45? The answer is no, because the PMF that is associated with 45 is concentrated at 45, so split from 39.5 to 45.5, sorry, 44.5 to 45.5. Okay. So what I will do is very simple. I will exclude the 0.45, and not only exclude the 0.45, I will go half a length below 45. Therefore, I will approximate it with continuous random variable which is less than or equal to 44.5. It should be very clear in your mind. You should never get confused in this kind of trap. Now we will take the similar trap which is similar to rule 1, but with a greater than or equal to sign. What will happen to this? Again, greater than or equal to 45 means 45 is included, correct? If 45 is included, that means when I am talking about greater than or equal to 45, I should exclude 45 in this greater than or equal to sign. 45 is included, so included in this other complementary inequality. So this is very important. If you include, because this greater than or equal to 45, if you equate it with y greater than or equal to 45, then what you are accounting for, that half length that is distributed for 45 is accounted in that probability computation. You do not want to do that, right? So it is y greater than or equal to 44.5, because I do not want exclude 45, which is logic similar to rule 2, but with greater than or equal to sign. Now comes the rule 4, which is actually equivalent to rule 1, where you are saying probability of x greater than 45, so I will not have 45, so I will go half a step above 45, which is 45.5, and then I will ask, it is essentially equivalent to saying probability of x greater than or equal to 46. So we have to exclude 45, and then I will write that continuous approximation as y greater than or equal to 45.5. These are minor subtle steps, but if you do not follow them properly, it may lead to wrong calculations, particularly given a discrete random variable as a loss distribution. Okay. So now you, if you want, you can pause the video, memorize these 4 rules properly, and then come to the problem solving drill. Now this one step inclusion of this our 4-step drill for this continuity correction. So I will have a 5-step drill. So just pause the video, view these 4 rules, and then answer the question which will come now, and then come back and start the 5-step drill. So let us move on to the 5-step drill. We will add one new step to our 4-step CLT process which we discussed in lecture 2. So first we have identified that the random variable is discrete. We have a problem of x less than or equal to k. Identify n, mu and sigma square. For Bernoulli or Poisson distribution, its some parameters will be n mu, n sigma square, nothing changes. Continuity correction is a new step. because we are approximating discrete with continuous. So, we will approximate it with continuous, which is y norm less than or equal to k plus 0.5. So, this is what approximation correction is. Then you simply standardize with this 0.5 correction and solve the problem as usual. So, this is our basic setup. Let us take up one problem and see how it works. So, this is for less than or equal to setup, which is rule 1 that is applicable here. Okay. So, x follows binomial 100 with success probability of 0.5. I want to find probability of x less than or equal to 45. Rule 1, less than or equal to 45. So, what should I actually find for? So, it's, you can see this way, this is a 0.45 and I have a probability mass associated with this 0.45 and this is say 0.5 interval around this, and the graph of continuous curve goes something like this around this point. So, I will actually accommodate, this is 44.5 and 45.5. So, I have actually distributed the probability mass. This is just an approximation. So, I have actually distributed this probability mass. Ideally something should happen like this. So, on these edges, other edges, okay. So, this bar that you are seeing is also distributed on these edges, and now what should we look for? If I am looking at x is equal to 40, x is less than or equal to 45, I should look for y which is less than or equal to 45.5. That is the idea of rule 1, right. So, remember this at the back of your mind, and then we will assume this problem solving drill as usual x. So, I really do not worry about continuity correction at this stage. First of all, I will worry about whether central limit theorem is applicable. N is equal to 100, it is applicable. Can I compute the mu for this? Yes, I can compute mu for this. Can I compute variance for this? Yes, I can compute variance for this. Mean is going to be p, which is 0.5. Variance is going to be p into 1 minus p, which is 0.5 into 0.5, which is 0.25. Sum problem. So, I have mu s, which is n mu, and that will give me the sum to be equal to 50, sigma s square, which will be n sigma square. So, you just use that 100 times sigma square and it will give me sigma s to be equal to 5. So, we have identified mu s, we have identified sigma s as well, and we have actually looked at a binomial distribution which is essentially sum of Bernoulli random variables, right. So, this is essentially the distribution of the sum x, and then the continuity correction step comes, which I have motivated enough, and it is actually y norm less than or equal to 45.5, correct. This we have had enough discussion. So, what we will do now? We will simply put everything in the context. We will standardize this normal random variable 45.5 minus 50 divided by 5, and I got minus 0.9 to be the z value for this particular thing. So, probability of z less than or equal to minus 0.9. As usual, this minus 0.9 will not be visible in the normal table. So, what we will do? We will look at the logical complement of it, which is 1 minus phi of 0.9, and that phi of 0.9 turns out to be from normal table 0.8159, which is equal to 0.1841. Okay. So, I have solved the problem. So, what is the problem now is we have the answer that probability of x less than or equal to 45 is going to be 0.1841, and this is a classical case where we are actually approximating binomial distribution by a normal distribution. We can actually prove this as a result that any binomial distribution which is close to half can be very well approximated by normal distribution with lesser error, and in general any binomial distribution can be approximated with normal distribution. Okay. Let us now go and level up the game. Instead of having binomial, let us have Poisson random variable. Logic is identical. CLT will work when lambda is large. So, let us say lambda is greater than 20, that is our baseline, because binomial distribution can also be approximated by Poisson. So, we need a larger lambda, and that is the baseline that we require. So, in this case naturally x follows Poisson with lambda equal to 64. You are asked to find probability of x greater than 70. Okay. So, we are saying we can approximate Poisson distribution with normal distribution. Okay. So, how will you handle this? We need to compute what are n, mu and sigma square and whether CLT is applicable or not. So, CLT is applicable because lambda is greater than 20, therefore, it is a matter of computing mu s and sigma s square. Here imagine that this Poisson is a distribution of sum, okay, that is the key idea, or you can take it in this way that x1 follows Poisson with lambda 1, x1 follows Poisson with lambda 1, and you are actually taking a sum of 64 IID Poisson lambda equal to 1 random variables. Okay, that is the intuition that you require. So, if you have that particular thing, where I have used actually the result that we have proved in MGF, where sum of two independent Poisson random variables is again going to be Poisson, that is the result. So, if you apply that result, then you have to compute mu s, which is expected value of x, that is again lambda. Because it is Poisson, mean is equal to variance, so variance is also 64, and therefore the standard deviation is going to be 8. Now the question is the continuity correction, x greater than 70, it does not include that point 70. So, where should we stop? That is the idea, right. Shall I go to 69.5 for stopping this? Then I am actually including it in that probability calculation, right. So, this is not a correct answer. Then shall I do it for 70.5? Is that the worth the answer? Yes, because when I look at the point 70 and the interval around 70, this number actually goes up to 70.5 for approximation. This will go to 69.5. So, when I split over this density will be split over 69.5 to 70.5. So, the greater than or greater than 70 will have an approximation which is y greater than 70.5, right. So, these two are approximately equal events, that is the idea. So, if you get that idea, then this particular thing is very clear. Your y norm is going to be greater than or equal to 70.5, right. So, I missed that equality step which I am putting now, it is greater than or equal to 70.5. So, this continuity correction you apply and then you calculate the probabilities. How will you calculate the probabilities? Again standardize Z score. So, do that Z score with this continuity correction, which is 70.5 minus 64 upon 8, it will give you 0.8125. This is very nice. I have probability of Z greater than or equal to 0.8125, which is 1 minus 5 of 0.8125. You can easily calculate it using the normal table, and it turns out to be 0.209, which is 20.9%, correct. So, now we will actually give some inclusive exclusive mnemonic to memorize for these 4 rules. So, first inclusive, let us say less than or equal to or greater than or equal to. So, whenever that less than or equal to comes, move into the interval, that means less than or equal to 45 means y should be less than or equal to 45.5. Okay. So, we are moving into the interval, inside the interval, right. So, when it is x greater than or equal to 45, you will step behind, that means y greater than or equal to 44.5. So, you want to include the bar so that you make the area bigger, that is the actual point that you have to take. Okay. What if we have greater than or strictly less than? You have to move out of the interval. You do not want to be in that interval of that number. So, x less than 45, I do not want to be. So, I will keep a space away. So, it is 44.5, y less than or equal to 44.5. If x is strictly greater than 45, what you will do? You do not want to be part of that number, right. So, because it is greater than, so you will move ahead, which is 45.5. So, y greater than or equal to 45.5. So, if you have strictly less than or greater than signs, you move out of the interval by 0.5 units. You are excluding that bar so that the area is becoming smaller, that is the idea. Still, if you have doubts, you will always draw a number line, check where you are, whether you are including or not, and check what is asked. That is the main idea, and if you follow that, you will never lose a single mark on this continuity correction problems, which are inevitable in your exam P. Okay. So, here is the summary of what we have done. What we have done is the correction error that appears when approximating discrete random variables to continuous random variables is mastered today. How you mastered? You have introduced a new tool, which is shifting boundary by 0.5 to capture the correct bars. What did you do in that? So, you have included that continuity correction steps in your CLT drill, where you have applied you have the 4 steps, and the third step that is applied is 0.5 continuity correction. Apart from that, you must have memorized by now that the 5 step drill includes find n, mu, sigma square, associate it with sum, mu s, sigma square s and sigma s. New step is 0.5 correction, then you standardize, then use the Z table, do appropriate algebra to get the answer. Algebra is very important. So, what we have now with this lecture is a complete CLT toolkit. So, what we will do that with that CLT toolkit is we will move to full aggregate loss drills using these 5 steps and solve some exam style problems in upcoming lectures. Thank you.